On BBC One, Hale, Bopp, we salute you. In the Sky at Night.
Good evening. Our 40th anniversary programme last month was graced by a bright comet, Hale Bopp. But 40 years ago, in April 1957, our very first Sky at Night programme was also greeted by a bright comet, Hale, the famous spiked comet. It was a bright, naked-eye object, and which I may say will never return. It's been thrown out of the solar system permanently. But Hale Bopp was a great comet. Discovered in July 1995 by two Americans, Alan Hale and Thomas Bopp, hence the name. It was then a faint smudge of light in Sagittarius. But it was a long way away, more than 650 million miles from the Sun, and you don't normally see comets as far out as that. Therefore, this was a very big comet indeed. It didn't reach perihelion, it's closer to the Sun, until April the 1st this year. But before that, last year, we had another bright naked-eye comet, Hale, and it was distinguished by its lovely turquoise blue colour. Now, that was in fact a small comet, but it came close to the Earth, within 10 million miles of us, and by cometary standards, that's very close indeed. Unfortunately, Hale Bopp, a much bigger comet, didn't come within 120 million miles of us. All the same, it was a superb object. At this stage, I'm delighted to welcome back Dr. John Mason. John, first of all, what determines whether or not a comet is going to become really spectacular?
Well, all comet activity, of course, stems from the dirty ball of ice at the heart of the cometary nucleus. And the larger the nucleus, then intrinsically the brighter is the comet. If we look at comet Hale, we can see that the nucleus is only some 2 to 3 kilometres across. You can see it there compared to the Isle of Wight. In the case of Halley's comet, which is quite large by cometary standards, the nucleus, elongated, is some 16 kilometres by 9. But in the case of Hale Bopp, the nucleus is 30 to 40 kilometres across, so it really is a giant. The other factor that's important is how active the nucleus becomes, and the activity of the nucleus was shown very clearly by the Giotto images of the nucleus of Halley's comet. The nuclei of comets are enshrouded in a dark crust, blacker than soot. And as the sun warms the crust cracks, exposing the underlying ice to view, and the gas and dust spurts out as jets through those cracks in the crust. Now, in the case of Halley's comet, only some 15% of the nucleus surface is active. But in the case of Hale Bopp, we were dealing with a very, very active comet indeed. And as you can see here, it put out multiple streamers of dust, indicating that the nucleus was very active indeed.
What a pity it didn't come really close to us.
Yes, indeed. Hale Bopp is intrinsically the brightest comet to have come inside the Earth since the Great Comet of 1577. And if only Hale Bopp had come as close this year as Hyakutake did last year at its brightest, then Hale Bopp would have been as bright as the crescent moon. Its tail would have stretched right across the sky, it would have cast shadows at night time, and it would have been visible in broad daylight.
As some past comets have been. Remember the Great Comet of 1811.
Yes, there are some similarities between Hale Bopp and the Great Comet of 1811. Both were visible with the naked eye for a very long time, and similarly to the Great Comet of 1811, Hale Bopp was well to the north of the Sun when at its best. In fact, although their orbits are quite different, their perihelion distances, orbital inclinations, and their revolution periods, well, they are actually very similar. If we look at the orbit of Comet Hale Bopp on this schematic, you can see it was discovered out near the orbit of Saturn, and then as it came closer, it moved well to the north of the Sun. And here in a close-up, you can see on the 1st of January, the Earth and the comet were on opposite sides of the Sun, but then at perihelion, the comet is now well to the north of the Sun, not particularly close to the Earth, but well placed, visible in a dark sky. And then the comet moves steadily southwards, it crosses the ecliptic plane on the 5th of May, and then into the southern hemisphere.
Luckily for us, the tails were well presented.
Yes, it's always rather disappointing when, because the orientation of the tails relative to our line of sight is not good, there is a certain amount of foreshortening, and we don't see the tails to best advantage. In the case of Hale Bopp, of course, we got a magnificent view of the tails. This photograph of the comet, taken on the 20th of March by Rob Bullen, shows the gas and dust tails very clearly. The gas tail is the tail you can see pointing almost upwards there. That consists of gas blown backwards from the head of the comet by the solar wind and excited to fluoresce with a sort of bluish light by the solar ultraviolet radiation. On the right there, you've got the broad curving tail, and that consists of dust grains pushed backwards from the head of the comet by radiation pressure, and because that reflects the sunlight, then the dust tail shines with a yellowish light. Now, the changing appearance of Hale-Bopp's tails was quite apparent due to the varying orientation of the tails and the changing positions of the Earth and the Sun and the comet. And, in fact, initially the gas tail was well presented, then the angle changed and the dust tail was visible as well as the gas tail quite easily, and then the dust tail swung round in front of the gas tail, more or less hiding it from view. The changing appearance of the tails is well shown in this sequence of 4 views by Martin Moberly. You can see here in this picture taken on the 15th of February, the gas tail is rather narrow on the left there, just visible, and the dust tail is not really very active at this time, and there's a dark lane between the two tails. Now, by the 13th of March, you can see that the gas tail is now broader and much more highly structured, and the dust tail is really beginning to become prominent. By the 30th of March, the day before perihelion, the gas tail is strongly blue, the dust tail is very bright and obvious, contrasting strongly with it. And by the 9th of April, the iron tail or gas tail is not so easily visible, and the dust tail is swinging round in front of it. And you can see in this view, taken on the 12th of April by Rob Bullen, that the curvature of the dust tail, very, very apparent. And at this time, the tails were swinging anti-clockwise at about 1.5 degrees per day. And of course, in early May, the comet went through the ecliptic plane. It then became much more susceptible to variations in the solar wind, and we then started to get complex structures in the gas tail and even a disconnection event. Now, the other interesting feature in the dust tail were the multiple fine striations or synchronic bands. And you can see here in this picture taken by Martin Moberly on the 17th of March, in the top right of the picture there, you've got these striations in the dust tail. Those are the synchronic bands. They're not so well seen there, but they were very well seen in West's comet of 1976. And you see this magnificent picture, and the synchronic bands are well shown there. And normally these are only seen in comets that come closer than 75 million kilometres, but in the case of Hale-Bopp, they were visible at twice that distance.
Then Hale-Bopp surprised us all by developing an entirely new kind of tail. It hadn't been seen before.
No, this was an exciting discovery, the discovery of a third tail, a tail of neutral sodium, a metal. Now, these two pictures show the neutral sodium tail on the left and the gas and dust tails over there on the right. The neutral sodium tail is the very, very straight, narrow feature with the sharp edge in the left-hand frame going from centre bottom up to the top left. And on the right, you can see the gas and dust tails. Now, the neutral sodium tail was photographed using a filter that allows through the light of sodium atoms but blocks out most other light. Now, the sodium atoms have a very short lifetime, so they couldn't have been released directly from the nucleus. We think they were either released within the coma from some parent that we're not too sure the identification of, or also released from dust grains within the dust tail. And the sodium atoms are travelling away from the head of the comet at 95 kilometres per second. That's 340,000 miles an hour.
We know that meteors are cometary debris, and comets leave trails of meteors behind them. Do you think we're any chance of a meteor display connected with Hale-Bopp?
Well, it's an interesting question. The dust particles that were released from Hale-Bopp at this return, in order to see those when we pass closest to the comet's orbit next January, we would have to pass much closer to the comet's orbit than we are. We're actually missing it by 15 million kilometres, which is too far. As for the dust which was released last time round, just over 4,000 years ago, we think that's probably too dispersed to produce a display of meteors, so I'm afraid I don't think there's much chance of a display of Hale-Boppids when the Earth passes close to the descending node of the comet early next January. Still, it'll be worth going out to have a look.
It was a very dusty comet, and there was a great deal of structure in the coma.
Yes, Hale-Bopp has been extraordinarily active, and that activity was apparent as long ago as September 1995, when the Hubble telescope took this image of it. And you can see that great spiral of dust there, and at this time the comet was still 1,000 million kilometres from the Sun. And the Hubble telescope obtained a series of pictures of the comet between June and October last year, and it showed the development of the inner coma and particularly dust streamers within it. Unfortunately, the Hubble telescope hasn't been able to image Hale Bopp when it's at its best because it's been rather too close to the Sun, less than 50 degrees in elongation. But we have had some excellent sequences of CCD images from amateurs. Here's a superb series of 6 pictures in false colour from Nick James, taken between the 16th of January and the 13th of March. And if we run through them one by one, you can see the changing structure in the inner coma, the changing position and location of the dust streamers. And I suppose one of the most striking features has been the formation of a great dust streamer to the southwestern side of the nucleus, and you can see it there pointing out towards the top right of the screen. And in many ways, these features resemble the streamers seen in the inner coma of other comets. For example, Halley's comet in 1835. You can see in this picture what those streamers look like. Now, another important feature has been a series of equally spaced concentric shells on the sunward sides of the nucleus. Some people said they look like ripples in a pond. And if we look at the arcs produced by the brightest jet, we can see that the nucleus was apparently rotating clockwise before February, but clearly anti-clockwise in March. And the spiral form of the streamers, well, they were more or less straight around about the 1st of March. And what we think happened is that our viewpoint has moved from the southern hemisphere across the equator to the northern hemisphere of the nucleus, with the active spot being in the northern hemisphere of the nucleus. And we can see the rotation of the nucleus very clearly in this superb movie obtained by Terry Platt on the night of the 28th, 29th of March. And you can see the anti-clockwise rotation of the nucleus very clearly. It's spinning in a period of 11¼ hours. And the shells are expanding radially away from the nucleus at 300 metres per second. That's 1,100 kilometres per hour. And the dust jets are actively ejecting material when they're facing the sun. They then shut off when they're in darkness. And this alternate periods of activity and quiescence produces the concentric shells. And you can see in this animation, as the nucleus rotates anti-clockwise here, the shells are coming off one by one, the youngest closest in and the oldest further out. And these are very similar to the shells seen in, for example, Donati's comet of 1858, you can see them there. Also Coggia's comet of 1874, that also had these shells. And less obvious, Comet Swift-Tuttle, the parent of the Perseid meteors, in 1862.
What about spectroscopic observations of the nucleus?
Well, of course, here, spectroscopic observations began when the comet was still a long way from the Sun. Here's a spectrogram obtained on the 3rd of September, 1995. And, of course, more than 30 different atoms and molecules have been identified in the comet, and over 20 of those contain carbon. We've got carbon dioxide and carbon monoxide. We've also got hydrocarbons, methane, ethane, acetylene, and hydrogen cyanide, formic acid, formaldehyde, and even methyl alcohol. Observations of the hydroxyl emission rate show us that the comet was releasing 130 tonnes of water a second. That's 39,000 gallons of water a second. It was also releasing 1,000 tonnes of dust a second. And to put that into perspective, that's 20 times the water that Halley's comet was putting out and 200 times as much dust at the same distance from the Sun.
What can you say about the origin of Comet Hale Bopp?
Well, the spectroscopic observations have helped us here again because the discovery of heavy water has helped us. Heavy water is ordinary water, H2O, with one of the hydrogens replaced by deuterium, heavy hydrogen. And the ratio of deuterium to hydrogen in Hale Bopp is 1 part deuterium to 10,000 parts hydrogen. And that's very similar to what we find in the Earth's oceans and the atmospheres of the outer planets. And it tells us that Hale Bopp is a normal comet formed in the outer parts of our solar system, just like Comet Halley and Comet Hyakutake.
Well, I think we can say now quite definitely that Hale Bopp has been a great comet. How would you reckon it compares with the great comets of the past? I mean, those that were seen long before our time.
Well, it's difficult to assess. One way we could look at it is the peak brightness reached by the comet. Now, Hale Bopp attained magnitude -1 at brightest, which is quite bright, but by no means exceptional. For example, even in the last 40 years, we've had 2 other comets brighter than that. We had Comet West of 1976, and of course the superb sun-grazing comet Ikiaseki of 1965. But neither of those were visible in the dark sky, although they were brighter. We also, of course, early in the century, had the great January comet of 1910, the daylight comet of that time. So there have been several other comets brighter than Hale Bopp. Another way we could look at it is the length of the tail. Now, the maximum length of Hale Bopp's tail on April the 9th was about 40 degrees. Again, this is quite respectable, but by no means exceptional. Comet Hyakutake last year had a tail some 70 to 80 degrees in length. And earlier this century, Halley's comet had a very, very long tail, quite magnificent. And if we go back to the last century, to the great comets of the 19th century, for example, the Great March Comet of 1843, well, that had a tail much longer than that of Hale Bopp. But there are 2 ways in which I think Comet Hale Bopp really is exceptional. The first is the length of time for which it's been visible with the naked eye. It was first visible with the unaided eye in June 1996, and we expect it to still be visible with the naked eye in October, November at the end of this year. That's a period of 17 to 18 months, which is quite incredible. Another way in which Hale Bopp is exceptional is the amount of time it's been visible at greater than magnitude 0, in other words, a negative magnitude object. Now, bright comets of the past, like the Great Comet of 1577 and the multi-tailed de Chazos comet, seen here, visible in 1744, they were visible at negative magnitude for about 6 to 7 weeks. Well, Hale Bopp has been a negative magnitude object for about 7.5 weeks. It peaked on the 28th, 29th of March, and it was greater than Mag 0 between the 3rd of March and the 24th of April. So Hale Bopp really is one of the most spectacular comets of the past 400 years.
Well, sadly, we've now lost it. In May, it went down into the twilight. This picture by Rob Bullen showed it, and now it's gone south. And although southern hemisphere observers will see it for some time yet, I'm afraid here we've seen the last of it, and I'm very, very sad to see it go. John, thank you very much. You know, last time it was round, the pyramids were being built. And here's a picture by John Goldsmith showing the recent return over a pyramid. And what about Stonehenge? And here, another Goldsmith picture, the comet over Stonehenge. But let's end up now, shall we, with a selection of pictures. And first of all, I must show one of my own, I think. There's the comet as seen from Chelsea, and my astronomical weather vane to the left-hand side lower down. Here's one by Andrew Brakes, taken from South France. The comet was seen from London. This picture by Chris Lloyd shows it nicely. Robert Ashby saw it from Antrim. Paul Doherty saw it from Stoke-on-Trent. And back to Stonehenge, a lovely picture taken by Paul Sutherland. From Neath, by Chris Lewis. From Kidderminster, by Chris Medley. And finally, by Trim Schroeder, a picture showing the comet against the background of the Northern Lights. So, goodbye, Hale Bopp. When we see another comet like you, I do not know. Now, don't forget, if you want the latest astronomical information, dial up our information line, 0891 83330, or dial up CFAX, page 620. And when I come back next month, we're still going to stay in the solar system and talk about Mars, the red planet, now high in the sky in the south after sunset. And this is a very good time because 2 probes are on their way there. The Pathfinder probe should reach Mars on July the 4th, followed in September by Mars Global Surveyor. So Mars is very much in the news, and I'll be joined next month by Dr. Peter Cattermole, and we'll give you the latest information. So until then, good night.